Hello everyone, James here again with another exciting Bio 279 lecture. Today we're going to go over an introduction to chromatography and the fundamentals of chromatography. I'm trying to keep these slides down to 10 to 12 slides a unit so that it doesn't get too confusing. What is chromatography? Chromatography, simply put, is just a means to separate a mixture into its components. That mixture could be DNA, could be RNA, could be protein and RNA, could be different proteins, molecules, and the most classic demonstration of this was by a botanist named Mikhail Zvet. He invented chromatography, and the reason it's called chromatography is because he was a botanist by training, and he was separating the different pigments coming out of plants that he was working with, and they were called chromophores. They were the first chromophores defined, hence the reason why we use the word chromatography. Chromatography typically has two phases. Actually, it always has two phases. The separation is based on the differential partitioning between the mobile and stationary phases. On the left here, we can see that in the case of paper chromatography, and you should pay attention to this because this is going to be today's lab, what we're seeing is we've got solvent moving up the paper, a bunch of pigments moving up the paper at differential speeds and differential amounts and spreads depending on their solubility in the solvent and how they're moving within that solvent, within the mobile phase. So we've got a solvent front here. This is important to pay attention. We've got the solvent down here. We've got our pigments or our analytes here in the middle, and we are going to be focusing on the movement of those pigments in today's lab. The same thing applies for liquid chromatography. So you can see on the right here we have a typical liquid chromatography column setup. The mobile phase in that is your binding buffer, your equilibration buffer, your elution buffer. Any one of those buffers is considered the mobile phase whenever we get to doing bead-based chromatography. Okay, common stationary phases, thin layer chromatography, very similar to paper chromatography. Those two terms get used interchangeably, but there is a little bit of difference between the two in terms of solvents and what you're separating. Bead-based chromatography, which is the method that we are mostly focused on in this class for biomanufacturing. And there's another phase called membrane or monolithic based chromatography. We're not really going to go into that for the purposes of this course. Our common mobile phases in chromatography are gas and liquid. That's really all we have, is either gas chromatography or liquid chromatography. The liquid chromatography is, again, what we're going to be focusing on in this class. The liquids can be solvents, organic solvents, ionic fluids, pH-based fluids, buffers, and straight aqueous solutions. Okay, this is important because this is going to be in our exercise for the lab today. We are going to be calculating something called the retention factor. It's defined as the ratio of the distance traveled by the solute, or in this case, the pigment from the pen, to the distance traveled by the solvent. So we are going to be measuring the distance of the solvent front and the distance of migration of each one of these pigments for today's exercise. RF values are usually expressed as a fraction of 2 decimal places. And again, the common mobile phases here, gas and liquid. We're going to be working with water and alcohol, probably isopropanol, as our solvents in today's exercise. The calculation is right here at the bottom. Basically, we've got the RF defined. Here is the distance traveled by the compound over the total distance of the solvent front. So it's going to be the distance of one of these pigments divided by the distance of the solvent front. So here is an example of a calculation. For your reference, we will be calculating the distance moved and the retention factor of all of our pigments today. Okay, we're going to move into some fluid dynamics here for the duration of this lecture, and there will be some nice descriptive 1 to 3 minute videos that are posted on the channel that will be included in the link on the first page of this lecture series on the PowerPoint, and they have described these in video as best as or better than I can with the animations that they've used. So let's move on. Phase dynamics in chromatography. There's 4 things that we pay attention to. One is called axial dispersion. Another is called film mass transfer. Another is the interparticle diffusion or pore diffusion. And another is binding and surface diffusion. I'm going to go through all of these in this lecture, and we will revisit this in the lab section so that you can have a little bit more descriptive lecture with me using the whiteboard. So axial dispersion, it's basically the movement through the column and all of the beads of the column. And what happens is when we put pressure into the column and we're moving our analyte or protein through this column, eddies can be created. So we're pushing fluid here, but you can get this swirling effect called an eddy. Like if anybody's ever been out to the ocean and seen how waves crash on the beach and small eddies form, it's the same exact process in fluid dynamics on a liquid chromatography column. So that is essentially the description of axial dispersion. It's the axial dispersion coefficient is a measure of the degree of spread of an inert trace material along a tubular vessel's longitudinal direction. So what we're looking at is the difference between it going through the column versus it spreading across the column for axial dispersion. It's a fairly simple concept. Okay, now we're going to get into film mass transfer, or what's called the boundary layer. When we have beads in a column, now this is represented so that you've got your fluid going through the column this way, and axial dispersion is the first thing that happens when you load a column with an analyte or a protein, any kind of molecule. The next thing that happens is what's called mass transfer, or the boundary layer. The boundary layer is the layer of fluid where these particles, whether they be proteins, DNA, RNA, pigments, any other analyte you put through this, they are building up in this space in between the chromatography beads. That's what the boundary layer is. Again, these are concepts. They're concepts that you should know doing chromatography. We are not going to have a lot of math surrounding this other than just the retention factor. So, but these are concepts that you should become familiar with. Next, we're going to talk about pore diffusion. Pore diffusion is the phenomenon where the adsorbate is absorbed into the interior of the adsorbent particles with bidispersed pore structures. So what this means is we've got the bead, and now our analyte or protein, DNA, whatever it is moving into the pores of those beads. That's what pore diffusion is. And it's the first step to getting something on board in a chromatography bead, especially in size exclusion. But this also is applicable to ion exchange and affinity. because affinity chromatography, even though the pictures show that that the affinity molecules on the outside of the bead, that's sort of true. There are still some pores that the affinity molecule, the ligand, gets into. So now we're going to talk about binding surface diffusion. So now we've loaded the pores. We've started to load the pores. Now what happens is, as the analyte moves across our bead, there are pore structures within this bead, and we will get surface diffusion until we get equilibrium of that analyte across the pore structure in the bead. That's basically it. So we start out with loading our analyte onto the column. We get axial dispersion. It's going to go down through the column and then out. That's axial dispersion. Next, we're going to get the boundary layer. The boundary layer is the bead and the analyte, the viscous material that the analyte's becoming. It's becoming more concentrated around the chromatography bead itself. The next phase in fluid dynamics in liquid chromatography is we're going to get pore diffusion, where the analyte starts to move into the actual pores of the bead. The final piece of liquid dynamics and phase dynamics in liquid chromatography is the binding and surface diffusion of the bead itself and the analyte within that bead. So as it moves in through pore diffusion, then it will start to spread across that bead, and will reach equilibrium across the bead with however many particles move through that bead. That's the basis of chromatography. This is what we're going to be focusing on today in the lab. We're going to be using paper chromatography as a method, or as a model, for this, and I'm excited to see all you guys at 6 o'clock.